in the last class, I when I finished my lecture, this was the issue that I addressed there. So let me explain it again. Suppose you have an attribute where you have too many values. That means if you consider the number of discrete levels that you may consider, that number is significantly higher than other attribute values, other attribute domains. Now, in that case, it has been observed that the information gain is biased to this kind of attribute. For example, if you consider the dates, you may have birth dates, for example. So, there are 365 or 366 possible values. In that case, these attributes will have a higher information gain, and you can, this attribute will be selected. But the problem is that, as you understand that this will cause heavy overfitting of the data, and this is in fact a very poor predictor for the case. And so this is the reason that many small partitions that would likely to have low entropy and you have higher information gain. So what should you do in that case? So in that case, you have to normalize the information gain with respect to certain characteristics, certain properties of this kind of attributes. And what kind of property can you think of? When you have this kind of attributes where you have too many values in their domain, that means it has its domain is significantly larger. Size of its domain is significantly larger than the domain of the other attribute. So, what do you expect? What kind of normalization can you guess that would help you in removing this bias? Do you have any particular idea? Have you understood the problem? So I'm not getting any response from anyone else, it seems. So maybe I can ask someone like, say, Shubham Misro. Do you have any comment? Is Shubham there? No, it seems Shubham is not there, but no, though he's marked here. Let me see. Kshitiz is here.
Yes.
So
yes, sir.
So can you guess anything about this? That what could be characteristics of this kind of attribute, which is basically causing the information gain much higher? Do you have any idea or any kind of?
No, sir.
Okay, fine. So in fact, no. If I consider this kind of attribute, you can see that it's a very diverse domain. Diversity of the domain is quite high. So in that case, entropy could be a measure of once again that same entropy, but here the entropy would be on the attribute on the distribution of the values of the attribute itself, or rather I should say, distribution on the attribute space itself. So in the information gain, when we considered entropy, it was on the class distribution on the set, but here it is a distribution of in the attribute space itself. And suppose an attribute has say n values, n number of items. So what should be the highest entropy? What should be the max? What could be the maximum entropy? Anyone?
So it will depend on the number of labels.
I asked what could be the maximum entropy. So I told number of level is n log n. Yes, that's right. Log n base 2. Okay. So that is the maximum number of that is the maximum entropy. So as you can see that if your n increases, this maximum entropy also increases. Whereas no, if I partition it into small subsets, as I mentioned, that it is likely to have low entropy. So you see that these two are contrasting. That because of that problem, you will have a very high information gain, and that's why if I can normalize simply the information gain by the entropy of that attribute space, then I think we get a we get something useful. So that is what is done. Instead of absolute information gain, we consider another measure, which is basically gain ratio. So gain ratio, it gives you, you can see that there is a normalization factor which is called split information SA. Actually, this is nothing but the entropy over the attribute values, those attribute distribution of the attribute values in S. That is exactly you are measuring there. So let me define it. You can see that this is what is the definition. Do you agree that this definition, this expression is essentially measuring the entropy of the distribution of values of A in S? Suppose there are C values in the attribute set A. So for each value, you have SI disjoint set, and so you can see that cardinality is expressed here. So it is a fraction of that values occurring in that set. So that's the probability, right? That is just simply, it is same as sum of pi log pi kind of familiar expression. Of course, the interpretation of probability here, probability of an attribute value in the set. Previously, I mean, in the information gain, what kind of probability interpretation you consider? In the information gain, like the numerator, when you consider the computation of the numerator, that is gain SA. So what kind of probability measure you are using there while computing entropy?
Distribution of the labels.
So probability of the level. Yeah, you are right. That's right. So probability of the levels, and that is what you are considering in set S. So A is given. So that is one thing. And then given a partition, what is the distribution of the levels there also? For each SI, you find out what is the entropy in each SI with respect to class distribution. So this is the difference. So both are using a measure called entropy, but the implications are different. So this is what exactly that is further elaborating the definition of split information. And as I mentioned that essentially split information measures the entropy from distribution in attribute space. And this is what is penalizing higher number of partitions. And in this way, you try to normalize, you try to remove the bias due to the diversity in the attribute space, higher diversity in the attribute space. Now, there is another kind of problem that you may occur in the training example. Sometimes, some of the attribute values may be missing in the training examples itself. But in your unseen case, unseen observation, you may have those attribute values. You may have instances with those attribute values. So how do you handle that? How do you learn under that scenario? So that is the question here: how to handle missing values of attribute. And there are several techniques for that. I mean, using the training examples you carry on, that means at each node, for that testing that attribute, you have to consider these type of, these are certain techniques for missing value, handling missing value. So one of the method could be that you consider the most common value of A among other examples sorted to node N. Suppose it can have two types of missing values. One is that in the examples itself the values are not there. The other is that somehow due to noise or something else, that attribute value is not captured. Okay, so it's a kind of question mark on that attribute value. So this is the first scenario that no, if you have that kind of thing, that you have the values of other attributes, but no, just the attribute value on A is missing, then you can consider, given the input set, what is the most common value of A, and you can assign it. That is one kind of, I should say, bias or assumptions you are using there. Then the other one is that suppose you have the you assign most common value of A among other examples with same target value. So it is another way that previously it is just the most common examples of A, but you consider the whole data set, training example set, and you know what is the target value. Only the value of A is missing. So you find out what is the most common value of A with that target value in your whole training example data set, and then you can assign it. Or you can have some probabilistic way of inferencing, use the probabilities. Any question? Okay. So you can assign probability pi to each possible value of A, and then you consider the fraction of pi of example to each descendant node in tree. So in that way, you can consider. That means you consider that you find out what is the probability of value occurring in your whole distributions, and then if some values are missing at certain point of node, you can consider that distribution to assign these values and use them for propagating to the descendant nodes. So also they classify the test instances with missing values in the same fashion. So in those nodes, you have to consider this probabilistic interpretation of particular area. So this is used in the C 4.5 another decision tree algorithm. So we discussed mostly ID3, and C 4.5 is the better version of ID3, where all these problems are handled. And there is another case, another type of issue that occur, that is the cost of an attribute. So when you are applying or forming the decision tree, as I mentioned in the previous case also, that cost of using attributes, they may vary. Some of the measurements are less costly, some of the measurements are very high. So you know that I mentioned about this particular thing when you are considering the diagnosis, and that is very clear from the way doctors perform diagnosis. They may not suggest the costly tests, even though they have a better sensitivity and specificity because of the expenses. So they may go for in that their protocol, they may go for less costly given certain situations. So depending upon different situations, so it may be screening test initially, and then you can go for the more confirmation test if your screening test gives some indication, something like that. So how to learn a consistent tree with low expected cost? Here, once again, like gain can be also modified using this cost feature. That means higher the cost, information gain needs to be reduced. So you give more less weight to those kind of attributes, so that when you are selecting an attribute based on this information gain criteria, this cost is also taken into account. So this is one typical measure, one typical function which is used, like it is basically normalized by the cost, but gain has been given more weightage, as you can see. And also, so this is the name of the authors, the scientists who have proposed this. Another function is this. You can see the expression there. You can get gain as A and cost A. So these are typical functions where this omega is a constant in the range 0 to 1. It also tries to give weights between the cost and gain, relative weights. There is another interesting impurity measure that is used instead of entropy, that is called Gini index. And the definition of Gini index is given in this form, that in the attribute space, it's not attribute, basically as class distribution, as we were saying. So in the class distribution, it is the product of probabilities of the classes, of different classes, when the classes are not same. I mean, in the two class case, it is simply product of probability of one class into probability of the another class, which is if the class, suppose the class is EAs, another class is no, so and the probability of EAs is P, then the probability of no would be 1 minus P. It would be the Gini index of these two class things would be P into 1 minus P. That is a simple thing. And you can see that function again. That function becomes maximum when P equal to half. So that is the characteristics. And it is almost similar characteristics with entropy also. Entropy becomes maximum when P equal to half. You can see in the Gini index also it has similar characteristics. Of course, the functional form is different. But it is generalized, like entropy also, it is generalized with respect to multiple levels, more than 2 levels, where you get that expression. So you can consider the Gini index given the set, and again you consider Gini indexes of all the subsets. So in the same manner, you compute Gini indexes of all the subsets with partitions which are formed with respect to the attribute values, particular for an attribute, and then you take the weighted average of Gini index of all the partitions. Same, the weights are proportional to the number of elements in each partition. So it is the same expression. As you can see, this is what is expressed. What I mentioned exactly, that is what is being computed here. Maybe it has been shown with respect to probabilistic interpretations. But this probability of V is the probability of a attribute value of A, and which is given S, which is basically the fraction of times V occurs with respect to the total number of elements in that set S. Similarly, probability of I given V is the probability of class I in the partition induced by the value V, and probability of J given V is the probability of class J in the partition induced by V. So it's the same way you are computing. So now this is the Gini index, which is induced by the partitions, which is induced by the partitioning due to the attribute values of A. So the difference of these two will give you the gain in terms of Gini index, the same measure. And just to give you a better explanations of these computations. I hope that you have understood these computations, but just to illustrate further, you can see in this diagram, so there are different shapes and different colors. So colors are attributes and shapes are the class levels, right? So you have two shapes, triangles and squares. So those are the class levels. And you have three colors. So no, no, it is saying color, border, dot. Okay. Yeah. I mean, there are three attributes. Again, color has three values. Border has two types of border will have some values, and dot will have some values. Anyway, so those are the things, but we will be bothering on the suppose the color, because that is more prominent in the diagram. So let us take that example. So first, as I mentioned, that you have to consider class distribution while computing Gini index, like what you did for entropy. And so probability of square is 9 by 14. You can see there are 14 examples? 3, 3, 6, 3, 9. Yes, there are 14. And there are 2, 3, I hope there are 9 squares. And then there are 5 triangles. Okay. So probability of squares is 9 by 14. Triangle is 5 by 14. So Gini index of the this set, that input set, overall training examples should be 9 by 14 into 1 minus 5 by 14, which is once again 9 by 14. Sorry, for 9 by 14 into 5 by 14, not 1. So it is 0.230. And now you consider, for example, the color. Color as the attribute to attribute, and it has three values: red, green, yellow. And you can see these are the three partitions which are shown here. Partitions are shown where the class distributions are once again shown with the shapes. And you can see that the probability of first, the probability of red, probability of green, and probability of yellow has been shown. And then in each partition, you can compute the Gini index, right? So that is what we will be doing. And in fact, this is what, that is the Gini index of color. So the gain of Gini index using color is, in this case, is 0.058. So this is how it is computed. And you can do it for all other cases where it is not very clear from the picture, but if you get the attribute descriptions, then you will find that you get the Gini gain. And also you are using gain ratio, like you are using gain ratio and also Gini gain, both you are showing. Basically, gain ratio is computed by normalizing it by considering the diversity of the attributes, that is entropy of the attribute, in the same way. Is there any question?
Sir, can you give some intuition on how does this Gini index measure the same thing as entropy?
Exactly not same thing, but it's an
Good.
impurity. I just tried to mention you that in a Gini index, actually, let me use the. So in the Gini index, if you look at the function plot will be something like this. If I consider two classes, that means with respect to probability P, if you vary P for a two-class distribution, the maximum would be at P equal to half. Is it clear? That class distribution. So like entropy also, entropy is getting maximum here. So it's a kind of convex function you will get Gini index. Now this is reflecting that it is showing the impurity measure. This is showing the kind of diversity in the data set, in the class distribution itself. So if the class distribution is skewed, what you want, then Gini index would be low. If the class distribution is more diverse, that means random chance, that is, I should say balanced, then it would be higher. Is it okay?
And how are we comparing the initial Gini index and after splitting the Gini index? So how are they both compared?
I think this computation has been shown
Yeah.
here. Can you see that?
Yeah.
So sorry. Mm, yeah. So this is the initial Gini index. If you consider the class distribution of the whole set, so this is the probability of, say, class square, and this is the probability of class triangle. So Gini index is the product of these two. Okay, is it clear?
Yeah.
So then you consider, say, the attribute color. So you are considering this attribute color, and you know how many partitions color is doing there, because color has three values. Say red, probably red, green, yellow, right? And in the red, suppose the value, you have 5 elements. Um, suppose this is green. I'm not sure. You have to consult that diagram. But suppose these are the cases that these 14 samples, input samples, are partitioned as 5, 5, 4. Okay, with 3 color values. So in each one, this is the Gini index of the class distribution. Is it clear to you?
Yes.
So now they are weighted by the corresponding probabilities of each attribute value.
Yes.
So it is the weighted average. So you have, this is the Gini index of the partitioning. It's the same as what you did for information gain using entropy. It's the same. Principle is same, only computation is different. You are not computing entropy, you are computing Gini index. And then this is the gain.
Yes, sir.
Okay.
Sir, why are we choosing the attribute shape as the Gini index? Because it's maximum.
Why I am choosing attribute shape
As the Gini index of the entire class rather than Gini index with respect to shape.
I don't get your question. I mean, I have never talked about shape here. Are you considering that why rectangle and square, rectangle and triangle should be considered as two different classes? Is the question? Is it that question?
No, sir. I'm asking why are we considering the original Gini index as 9 by 14 and 5 by 14 and not the Gini index? There are two attributes here, right? Shape and color.
No. It is not. It's not shape and color. It is the class distribution. See, Gini index is defined on the class distribution. So class distribution. What are the classes? Shape is not an attribute there. Shape is shown as a class.
Okay.
Okay, square and triangles, they are representing classes. That's why we are showing with square and triangle.
Yes.
If you go through that, you see that classification, triangle and square. So these are the classes. That is the definition. Whereas attributes are color, border, dot. So this border and dot is not well explained in this particular sketch, right?
Okay.
Okay, fine. Okay, so let me then proceed with the regression tree issue. I mean, here it is almost similar to classification, but as you understand the levels, the output domain, instead of a few class levels, now you have quite a bit of larger range, larger size of the range, because you are going to regress, going to predict some values there. So you consider all of them as the possible levels kind of thing, right? So use a set of attributes to predict the value instead of a class level. That is the regression tree. And here now, instead of computing information gain, you compute the sum of squared errors, because you are regressing. So you are trying to match the functional values exactly as it is. Instead of considering the distribution, you are considering the values at that point given the instance. So the sum of squared errors, as you know, that is often used in regression, particularly least square error-based regression techniques. And the same thing, we use it here. So we consider while choosing an attribute, the criteria should be based on the sum of squared errors, which is the measure of the variances, if I say. So partition the attribute space into a set of rectangular subspaces each with its own predictor. So a regression tree is piecewise constant function, as you can see that since if it is a continuous, first thing, usually the attribute space may be it's in a continuous, the domain may be continuous. So you may have to have like the levels what you have for the continuous domain, and then when it predicts also, it predicts certain functional values. That is why the piecewise constant function. So this is one example for the piecewise constant function. And here the criteria is that to minimize the square error on the learning sample. So the prediction at a leaf is the average output of the learning cases reaching that leaf, which means you consider a leaf is homogeneous. Earlier, when you are considering a leaf is pure, when a leaf will have the same class levels in a leaf node, all the instances should have same class levels. But in this case, since it's regression and you are expecting variations and it is not well-defined levels, etc., and you will be rather predicting a particular value, some kind of average value over that set of examples, set of instances for the target values, whatever target values you have, you may have to predict the average value. So that could be one rational way of regressing. Now the variation in that target values, that means if you consider variance with the target values, and that variance you would like to keep minimum. So that is what you will be using as a impurity measure here. So this is what, as you see that impurity is defined over the variances. And if you have partitions given an attribute set, you observe, you consider all the partitions, and instead of measuring the entropy over the distribution of target values, rather we consider the variances there. So once again, it's the same principle. So what was the variance of target values in the original set, and what is the variances, weighted average of the variances in the partitioned set? So what is the gain in this variance? And you choose that attribute which has the maximum gain. That is exactly the strategy is used. You can see that this is expression, what is being used for this kind of gain. It is not really information gain, it is a gain in terms of the measure variance. You are trying to reduce the variance as you go on growing the tree. At each node, you are trying to reduce the variance of the partitions. Is it clear? This expression is clear to you?
Yes, sir.
So you can also use the pruning algorithms the way you have done in the previous case. Only your measure, instead of accuracy, it would be mean square error kind of measure. So that is what you have to minimize the squared error on the version space is selected. That tree is selected. And in practice, pruning more important in regression because full trees are much more complex. So pruning is more often used here. And often all objects have a different output values, and hence the full tree has as many leaves as there are objects in the learning sample. So this is the problem with regression. If you really try to make it consistent, it becomes almost meaningless. So and also it would be very large. So that's why it is suggested that you may have to stop at certain. So pre-pruning also strategy is, I think it is better, it is more followed here, although it is not written. That seems to me more rational. So when are the decision trees useful? So these are certain issues and also some variations of of the problem, decision tree for classification, decision tree for regression. So if I just summarize about the usefulness, so what are the advantages that you can see here? That it is very fast. It can handle very large data sets with many attributes in the schema. It is also flexible. That means several different kinds of categorical data, even the continuous valued data, all different kinds of data can be handled. It can handle missing values. It can accommodate classification and regression problems. So that is how decision tree is very, I should say, versatile kind of tool. It can handle versatile problems, and it has a good interpretability because it provides a set of rules that is very important. It provides a set of rules which you can apply over the data sets, over your instance space to get a decision. But what are the disadvantages? First thing is that the trees are unstable. That is, overfitting would be quite possible. That with certain amount of variation, certain amount of noise in data can give you completely a different tree, and it is not always competitive with other algorithms in terms of accuracy. That is a kind of observation that we note here, and we'll see later on. Another interesting thing what I considered that we can discuss also, that we have considered that decision tree can give me a set of rules, right? If you form a decision tree, then also you can derive a set of rules from the decision tree, and you can apply it for inference. What about if you want to learn rules directly from training examples? So is there any mechanism? In fact, there are algorithms for that. That is also a kind of problem. That means instead of forming decision tree, we may extract the rules, kind of rule mining issues. I thought, is it okay? The connection is now back. It is fine. But sometimes it was flickering. All of you can see?
Yes, sir.
Okay.
Yes, sir.
So you see that
Yes,
a
sir.
rule could be in the form of as you see if then kind of rule, and there is a condition and which we call conditional part, which we call antecedent, and then there is the corresponding application part of the rule. That means decision part, which is called consequent. So this is the kind of rule, and if we assume, I will give example of a particular type of derivation of rules, which is quite similar to rules. Format is quite similar to the decision tree format. There are different other forms of rules also. So we'll be restricting ourselves to the simple rules which are derived from decision trees. Similar kind of rules. Now we assume that antecedent in the form of conjunctive normal form, which is also true for the decision tree. That means every rule, they have an antecedent part, and then they have the consequent part in the leaf node. And antecedent part is the corresponding conjunctions of the attribute conditions over the path. So we consider, so this is one example. Say outlook equals sunny, and temperature equals high, and wind equals weak. And consequent part is the assignment of target attribute value. For example, play tennis equal yes. So one of the interesting algorithm that I will be briefly describing here, I will briefly describe here, and you can get the details from this reference. This is also from Michel's book. In chapter 10, you can find in the very beginning itself, this particular algorithm has been described. Actually, there are various variations. So it's a class of algorithms which called sequential covering algorithms. So the approach is that you learn rules one by one. So like in a decision tree, when you are learning a set of rules, after forming decision tree, you are learning a set at a time. So it's a kind of, I can give an analogy to it as if it's a parallel derivation of all the rules. But in the sequential algorithm, what we are trying to do, one by one, I will get a rule, I will apply it, I will find out how many training examples are covered by that rule. And then I will remove those training examples. Again, from the rest of the training examples, I will look for another rule which will best fit that. So the union of all such rules will give me the finally set of rules. So this is the kind of strategy when you are considering this kind of sequential covering algorithms. And there is a particular algorithm which is called learn one rule. So that is the essence. So learn one rule means that is the basic, I should say, that is the heart of this algorithm. If you can learn one rule from your training examples, then the rest of the part, that means by finding out that which are the instances in that example set are covered and then removing, and then again you apply the same thing. So it becomes trivial. Now there is a algorithm which is called general to specific beam search algorithm. So it starts with most general rule. So can you tell me that what kind of rule is most general in this context? If then clause what I mentioned, that which will cover all instances in the space. So in the antecedent part, see, when you say the rule, covering would be from the antecedent part, and consequent part, let us not bother. So we will be restricting our attention to the antecedent part. That means whenever a condition is satisfied for an instance, it is covered by that rule. Now, whatever may be the result output, let us not bother about that. So what should be, that means you are allowing everything. So clause is empty. So that is the kind of notion that in that case, we will write that particular rule as if empty, then some consequent. That in the rule, for a complete rule, there has to be some consequent. But for, as I mentioned, coverage would be, we will be considering antecedent part only. Now, what we do here in this learn one rule, in this algorithm, that is a general to specific beam search algorithm, it's a kind of greedy depth first search while forming this conjunctive normal form of attribute conditions. And always the attribute condition is given in this form. So attribute equals some value. So there is no question of giving a question mark, etc. All those things are not here. Like in the decision tree, in the discrete, if you consider all the levels are discrete, then also you have this particular condition. So the same way it is coming. So just to give you a brief outline of this particular algorithm. So as I mentioned that you have to consider the most general rule. And along with that, throughout your search process, instead of greedily searching for only the best fit hypothesis, you are considering a candidate list. And in the candidate list, you find out the k top performing rules. That means given the set of options at any particular moment, you can always find out the k top performing rules, and you can include it into your candidate list. And you go on updating this candidate list. So how you are doing it? So just that is what the next steps. That means if you consider each rule from your candidate list, we started with the empty clause. That means any attribute in the next level, any attribute present in your training example with some value will provide you one such particular condition of the clause. So you have to specialize. So this constraint, specialize that condition with a constraint of A equal to B by adding NCN. If I have a diagram, so I will explain with the respective diagram, but let me just give you the overall overview of this particular algorithm. So you consider all possible attribute value pairs in training examples. And each one of them will give a particular clause, and each one of them will give a different antecedents. And then using those antecedents, find out that how many examples are covered, or find some measure like how you can look at the other way, that the way you have looked at the decision tree, that means how pure is the partition with respect to that constraints also. That means you look at the class distribution also. Both can be done. In fact, in this particular algorithm, they suggested to use the class distribution. So they use simply the entropy. So lower the entropy value, better is the skewness of that distribution, and that is more favorable. So that is the strength. So that performance criteria is just simply the entropy of that particular training examples which are covered by that antecedent from the class distribution. So in this way, you have several possible antecedents at that stage. Out of that, you update the candidate list with k top performing rules. So what you are really doing, you are expanding a few such no few such because for each rule in the candidate list you are doing it. Suppose your candidate list contains say 3 rules presently. So for each rule you are performing these things, and then you are doing, and then you rank all possible conditions out of all these 3 rules, all possible new rules what has been derived, and then you again select the k top performing rules. And but you also maintain that which one is the best, rule at every step. That means you should also separately maintain that no, what is the best one, and then use that rule finally as your no as the result of your operation. That is the rule you have derived. And there, I told you that you are mostly concentrating on the antecedent part for covering the examples, whereas evaluating any rule, there you have, of course, considered also class distribution. And but when you are really going to form a rule, so once the antecedent part is selected as the best performing rule, then now you have to decide about what should be there in the consequent part, and there you assign the most frequent target value. So this is what general to specific beam search. You form the antecedent of the best performing hypothesis. So just an example. Suppose you have an empty clause. I told you that mostly you concentrate on the antecedent part, and then while evaluating a rule, then you consider the class distribution over that partition. So you start with single clauses in the beginning, and there are several options because of, as I told you, all possible pairs of attribute and values. And out of them, suppose so say outlook equals cloudy and say outlook equals sunny, that those are the 2 options which are, say your k is 2, so every time you are keeping the top performing, so say these 2 are considered, and you have to expand both of them. So I'm just giving example with respect to outlook equals sunny. Once again, you see that there the remaining attribute sets now you are testing. In your constraint, one antecedent is outlook equals sunny and temp equal high, then outlook equals sunny and temp equals low, outlook equals sunny and wind equals strong, outlook equals sunny and wind equals weak, and so on. And out of them, you choose what are the 2. In fact, not only these 2, even from outlook equals cloudy also you will find, and out of all this you have to choose 2. Just for the simplicity I have shown it like this, and you go on doing these things till you reach certain desired level of your impurity measure, that means low entropy value, and you can stop there, or you can have several other strategies. So several variations are possible. So these are I'm just discussing the principles, and you can get also much more details from the book. Please read that book. So as I mentioned, you have to form consequent assigning maximally occurring target value in covered examples. Is there any questions about this particular rule mining algorithm? That other than decision tree, in fact, you can directly derive rule from training examples. And as you can see also, this algorithm also has some kind of tree explorations over a search space of antecedents. So just to summarize the history of decision tree research, just to have some ideas that you can see it is quite old, concept learning came in 60s, then ID3 algorithm came in 70s, and then there is next algorithms like CART, and there are variety of improvements after that. And then in 1993, C4.5, which is presently C5, which is, I think, the state of the art now. So those algorithms are used. Of course, now there are other variations, like as you see, boosting or bagging over DTs is a good general purpose algorithm. In fact, I will be quickly covering 2 things. No, I don't have that much of time. So maybe tomorrow I will cover these 2 interesting concepts, like what is beyond decision trees. what other things are possible using these particular simple concept of decision trees, how to make your classification more reliable, what kind of different variations are possible. So we'll have a very brief discussion on that. So that I will do in tomorrow's class in the morning. So with this, first, Sudipto, can you take attendance from your end? Just check.
No, sir. That option is only with you, sir.
Okay. So first, let me take the attendance.
Sure.
Fine. So is there any question on today's part? So tomorrow, in fact, we'll have a new topic that is on introduction to probability. After completing few remaining slides, which are only a few slide sets are remaining. So that is on this decision tree. Those concepts, as I mentioned, those issues I will discuss. Some ideas about the advancement over the decision tree techniques. Those I will discuss also tomorrow.